So, in last lecture, we had finished the necessary discussion required for understanding of chapter 1. And then we will move to chapter 3, that is the discrete Fourier transform, which happens to be rather one and only meaningful exercise in digital signal processing as regards to transform domain is concerned. All the Z transform, the discrete time Fourier transform, these things merely remain on paper and cannot be implemented. What is the reason? Can you give the reason? Discrete time Fourier transform it may be, Z transform it may be, they merely remain on paper and cannot be implemented because for the simple fact that those are continuous in nature and using computer it is not possible to work with them. Theoretically you may get some insight by studying these equations. Then further discretizing the discrete time Fourier transform gives rise to discrete Fourier transform. Further discretizing discrete time Fourier transform. Discrete time Fourier transform is a transformation of, what is the input sequence? Input is continuous or discrete? For DTFT. For DTFT input is discrete, output is continuous. It's a discrete sequence to continuous function. DTFT is a transformation of a discrete sequence or discrete time sequence into a continuous function. So it cannot be implemented. Then if we further discretize this continuous function, that is discrete time Fourier transform, it is called as discrete Fourier transform. However, to be exactly appropriate, discrete Fourier transform also merely remains on paper. It cannot be implemented using computer. What is the reason? Because what is the reason that discrete Fourier transform also cannot be implemented using computer? Discrete Fourier transform cannot be implemented using computer. What is the reason?
Because it is continuous in amplitude.
It is continuous in amplitude. Right? Therefore that cannot be implemented. So what we implement, that is the realizable thing on which we can work, is we cannot work with continuous sequences on computer. We cannot work with discrete sequence on computer. On what we can work is digital sequences. We work with digital sequences. Digital sequence is an approximated version of discrete sequence. Digital sequence is an approximated version of discrete sequence. Presuming that the availability of digitization is much more than sufficient, the approximation error is ignored. Then this digital sequence can be transformed. This digital sequence can be transformed into a continuous function or a discrete sequence. It is also not realizable. Therefore, what is realizable is digital sequence into a digital Fourier transform, which is never used. This word you might not have heard. Digital Fourier transform means it is digital sequence to digital Fourier transform. Actually what we have, a discrete sequence to a discrete transform. We have learned these things last year. When it is of finite length, sequence, its transform is also of finite length and it is invertible. Right? So when we implement, so we can perfectly on paper, means deriving the equations and performing all mathematical operations on paper without the help of computer, we can very easily prove that there can be 1:1 correspondence between a sequence and its transform. Means its sequence is a set of numbers. Sequence is discrete in time domain, or it is a sample domain entity. It can have multiple samples, each sample can have any value. So it is a set of numbers is transformed into another set of numbers. One set of numbers transformed into another set of numbers, and that is an invertible transformation if we meet some conditions. Right? But this cannot be implemented using computer. When we implement using computer, we are having its digitized version. This is also digitized. In such case, again a question rises whether digital sequence to digital transform is completely invertible or not. Whether digital sequence to digital transform is completely invertible or not. That can be a question which you can, if you have understood something that discrete sequence to discrete transform is invertible, then you may think on the invertibility of digital sequence to digital transform. So all these things I am specifically mentioning because we must have a very clear idea what we are studying and what we are implementing in practical. There should not be a gap between understanding and implementation. I hope that you are doing something in practicals. So now we shall try to enhance our knowledge on discrete Fourier transform. Do you agree with the first statement? We now try to enhance our knowledge of discrete Fourier transform. When we say that we will be enhancing our knowledge, we presume that we have knowledge. So, discrete Fourier transform actually emerges from discrete time Fourier transform. It is sampling of discrete time Fourier transform. It is discrete sequence is converted or transformed into a discrete time Fourier transform, which is a function of omega. Xn is transformed to x of omega. Then x of omega is sampled for typical values of omega, maybe 1 sample, 2 sample, 4 samples, usually the samples of 2 to the power something for computational convenience, 8 samples, 16 samples like that, and only those samples are used, other values are ignored. Whether this kind of sampling of discrete time Fourier transform is appropriate sampling or not can be a question to be considered. But rather than engaging ourselves into that discussion, we shall try our level best today, or I will try my level best today to teach. As already stated that you are supposed to maintain an appropriate decorum, which is what we can say, reflecting your maturity of the class. To what extent you are able to learn will be depending upon the outcome after the lecture. So, discrete Fourier transform is mapping of one set of numbers to another set of numbers. I am trying to explain discrete. Are you writing some tutorial? As I am trying my level best to teach, every individual must try his or her level best to learn. Despite my trying best to teach and you are trying best to learn, if you are unable to learn, then nobody can help. So we are trying to present discrete Fourier transform as an independent module. Means we will try to put forth it presuming almost near zero background. Even though you had passed the course of signals and systems, that happens to be a prerequisite, but even if somehow you might have forgotten, somehow you might not have understood well, but by going through the textbook, by preparing for examination in conventional style, you might have cleared the course. So we are presuming not much prerequisite and proceeding further. So this discussion is not connected to implementing using computers. It's discrete, means it presumes that a number can have any value. While implementing, digitization would be there. What are its effects, that we'll see later. But in discussion, that will not be coming into picture. So now we are presenting it. Discrete Fourier transform is now an attempt is being made to learn discrete Fourier transform as an independent module. So we make some presumptions. We have a set of numbers. We have a set of numbers. For convenience, we consider that set of numbers to be of the size of 2 raised to n. Means we can have 2 numbers, 4 numbers, 8 numbers. Like that we can work with. We have a set of numbers, number 1. So we will write the presumptions. 1. A set of numbers is available. A set of numbers is available with us. First presumption. The second presumption, which is most important, is which is very much important, that is, each number is an ordered pair. Each number is an ordered pair, or in conventional way we can say that the numbers are complex numbers. Numbers are complex numbers, or a number is a pair, or in other way the number is a position in 2D plane. Number is a position in a 2-dimensional plane. One-dimensional number is position on a line. One-dimensional number can be considered to be position on a line where there is only 1 degree of freedom. When we consider an ordered pair, we consider both collectively in the given order. That means that number represents actually a position in a 2D plane. The number taken to both numbers taken together in that order. So when we say ordered pair, 1 0 corresponds to this, 1 1 corresponds to this, 0 1 corresponds to this, half corresponds to this, half 1 corresponds to this, like that. So 1 0, this is 1, this is first axis, second axis. So first coefficient for the first component in the ordered pair, first entity in the ordered pair, second entity, 1 0. Half, half. Half 1, right? So it is a position in a 2D plane. So whenever what is required to understand more appropriately is whenever we get a concept of number, we should immediately able to visualize number by a position in the plane. Number is always a two-dimensional number. Means at third year of your graduation, I suppose that whenever we come across a number, you must always visualize a complex number or a number in 2D plane, a position in 2D plane, or an ordered pair. So whenever we say that I have a set of numbers, means I have a set of complex numbers. Is it clear now? So then it may be all real numbers, means all would be having their second component as 0. So suppose if I have say a set of 8 numbers, I have say set of 8 numbers. First number is 20, second number is 40, third number is 30, like that. Means to say that in conventional way numbers are 2, 4, 3, like this. Is it clear? But that second component is 0. So this is the original representation of the sequence. A set of numbers is called as the original sequence. It can be very much long. 8, 16, 32, 5. You can assume anything, 1024. It can be a very long sequence. Then, if you look at this sequence, the question will come, how can I look at the sequence? If the sequence is one-dimensional, I may plot. If the sequence is one-dimensional, I may plot like this. Now, you must have that much visualization that if you plot like this, the first number means you now must be in a position to visualize it to this extent. For the first number, what you are doing? First number you are plotting here. This was n axis, n0, n1, n2, and you are plotting the number. You were representing number by bars with the length of the bar or the upper position indicating you the value, and bar is just to provide you a feel. Do you think that the discussion which we are having is too preliminary and you are well exposed and well conversant with all the discussions? So now, instead of this bar chart, we must be able to visualize a 3D chart. So at n equal to 0, there will be this plane, and in this plane there will be some number, some value. Then another plane, there will be some other thing, like this. Is it clear? So the numbers are two-dimensional. So you look at the sequence. So when I look at the sequence, I must visualize that the numbers are spread. N I am having like this, and x0, x1, x2, like that they are spread. So when I look at the numbers, original sequence itself, I get some information. By looking at the sequence itself, I get some information that is called as spatial information. Spatial information means the original sequence directly represents the values at different ends. So that is called as spatial representation. that is called as spatial representation. Xn, it is a plot of xn versus n. The original sequence or the given sequence is the plot of xn versus n. For every n, I am having with me value of xn, which is an ordered pair. Right. Now, so even though it's a pair, it is represented by a single number in the form a plus jb. Say 3 plus 4z is called a single number. There is ordered pair 3, 4 is called a single number. This fact must be very well understood, because unless this fact is understood, this transformation is very difficult to what we can say perceive. With this now, with this, what we want, this set of numbers is to be transformed. This set of numbers is to be transformed in some way. Number one, then there can be a zero transform. A set of numbers is there, transform is zero, just like a blank answer book. Whatever may be the question, the answer book is blank. This can be an identity transform. Same is the answer. There are few students, what do? They write the question paper in the answer book. There will be random transform. Means that the answers do not correspond to the questions at all. So all these are redundant transformations. These are trivial transformations. These are the transformations not to be considered. Therefore, we must have a transformation. Transformation is not for the sake of transformation. Transformation is for providing the signal information in an alternative way. The transform is found out to explore. The transform is found out to explore some properties of the signal which cannot be visible in its original form. Transform doesn't add to properties. Transform doesn't change the properties of the signal. Transform is one-to-one representation of the signal. Being invertible, it very clearly indicates that no kind of modification is expected in transformation. So, transformation is providing me the information of some features of the signal in a more exhibitory way. When I look at transform, so what is transform? Again, it is a set of another numbers. But by looking at a transform, I get some information about the sequence immediately, which I might not have got otherwise. An intelligent guy may get. An expert doctor may be able to analyze without going for X-ray. But for a normal person like us, we cannot do that. You are busy in what you, it seems that you are finding the discussion too preliminary. So, what we aim at after this, so we are having a simple presumptions. A set of numbers is there. It is of finite length. We would not like to confuse ourselves and others by considering an infinite length sequence, which will never end and our transformation will never stop. So a finite length sequence of n. n usually, again usually it is not a precondition. It is not a precondition, but is usually 2 raised to, say something like usually a index of power of 2, usually 16, 64 like that. Then after this, we are trying to represent it as simple as possible. So we transform it into another set of n numbers. We transform it into another set of n numbers. We transform this into another set of n numbers. So and another set of n numbers is derived by linear combinations you make it pause.